So it is working. Okay. All right, let's try this one more time. When we first started this, I gave you kind of the generic, simple graph here. Now, if we talk about the derivative of this thing, what will the derivative of this look like, just loosely? Now, do you remember when we did the sine wave and I derived that the derivative was the cosine wave? But then what I did was I drew a sine wave and we just sort of estimated what the derivative would look like by just comparing slopes and things. And we came up with a cosine wave. Well, if the derivative is positive in here, then the derivative function should be above the x-axis. Would you agree that the derivative right here should be 0?
Yes.
The derivative right here should be 0. I am increasing, so my derivative should be, going in that direction. The derivative. So if the slope here was 10 units, then the derivative should be 10 units high. How about over here? Well, the derivative should be going up here also, because all of these slopes are positive. What about in this region? Aren't all the slopes negative?
Right.
So the derivative should be below the x-axis, shouldn't it? Which brings us an interesting thing. The derivative turns around. The derivative turns around right around here, doesn't it?
Yeah.
That weird point on my function is where the derivative turned around. So would it be safe to say that f prime is 0? My derivative has a horizontal tangent here. Not the function, but the derivative. So if this is motion, okay, I want you to think motion for a moment. All right, so I like to do this. I'm going to start here. I'm going to run as fast as I can, not all that fast, and I'm going to slow down because I don't want to hit the wall very hard. I'm going to stop for a brief moment, and then what? Start going the other way as fast as I can, and at some point I'm going to stop. Where is my speed 0? There and there. Where am I probably going the fastest? Maybe in the middle. But as I speed up, at some point I have to stop speeding up. Do you agree? At some point I have to start slowing down. So I'm going forward, and then maybe I'm speeding up. But if I think of when do I stop speeding up, when do I start slowing down, the change in speed is called what? Starts with an A. Acceleration. Acceleration has to do with speeding up or slowing down. When is my acceleration going to be 0? Probably right about here. I was going faster and faster and faster and faster, and then I didn't go any faster, and I started slowing down. There's a brief moment in time where I'm neither speeding up nor slowing down. When is my acceleration going to be greatest? You know what it is? Right about the time I hit the wall. When I've stopped moving, my acceleration is probably my greatest. When I'm moving my fastest, right there, my acceleration is going to actually be 0. Acceleration and speed are not the same thing. They don't go together. An acceleration of 0 in your car means you're in cruise control. You're driving at a constant speed. It doesn't mean you've stopped. No, it means you're driving at a constant speed. Oh, so when is my acceleration 0? When I'm speeding up, going to slowing down. Now, I'm going to give you a different analogy, a windy road. This is probably the simplest way to think about it. I'm on a windy road. My steering wheel's hard to the right. Now my steering wheel's hard to the left. Now it's hard to the right. Is there going to be any moment where my steering wheel is absolutely going straight? Probably around maybe about here. And maybe again, I don't know, about here. Do you agree that brief moment in time I'm neither turning right nor I'm turning left? Okay? So in terms of turning the wheel, there's a place where I'm neither going right nor going left. Now look at this curve. This curve is definitely bending downwards, isn't it? It's definitely pointing downwards. But what about on this side? It's pointing upwards, isn't it? How about right here? It's doing neither. This is what is called an inflection point. So it's like on the windy road. I'm neither turning right nor left for that brief moment. For that brief moment on the curve, I'm neither bending down nor am I bending up. For one brief moment. Now, is it a horizontal tangent right there? No. No, but that describes a lot about my motion. That's called an inflection point. And where did it come from? Where the second derivative was 0. Now, my graph is definitely going uphill, but it's slowing down, isn't it? My slopes went from steep positive to less positive to less positive to 0 to a little bit negative to big negative. All of my derivatives were getting smaller and smaller and smaller. So in this region right here, my second derivative is negative, isn't it? Because my derivatives are getting smaller. How about in this region here? I went from 0 to small positive to bigger positive to bigger positive to bigger positive. My derivatives are getting bigger here, aren't they? So in this part here, my second derivative is positive. At this point here, my second derivative is 0. So in this portion, there's a term we use. We say it is concave down. In this portion here, you're never going to guess what we call this guy.
Concave.
Oh, you guys are way ahead of me. It's called concave up. The word concave simply means bend. That's it. The second derivative is going to give you a numerical value that refers to how much the curve bends. The first derivative is going to give you a numerical value that refers to the slope of the tangent line. The second derivative has everything to do with how much bend there is. So you'd say this is a windy road, but at this point of the road, is it bending in either direction? No, there's no bend there. I went from turning right to turning left right there. Right here, I went from being concave down to concave up, right there. I change concavity at the inflection point. Now, if you have a line, does a line bend at all? No. So would a line have any concavity at all?
No.
That's a tricky thing. What is the equation of a line? Just the generic?
Y equals mx plus
Okay. What's the first derivative tell me?
the slope.
The slope of the tangent line. What's the tangent line to a line? Wouldn't it be the line itself?
Yeah.
The tangent line to the line is the line itself, and it gives me the slope of m. What's the second derivative?
0.
0. How much bend is there in a line? None. The second derivative gives you a numerical value that refers to how much it is bending. Isn't that kind of cool? So the first derivative tells me the slope of the tangent line, but it's a line. So it just gives me the slope. Second derivative tells me how much is bending. 0. It's not bending. That makes perfect sense. Hopefully it makes perfect sense. Okay? In Calc 3, we discuss motion in 3 dimensions. We're moving around in 3D. And so we always have the direction of the velocity, which is why I say when you hit the banana peel in space, which way would you slide? That's your velocity. Where are you going next is determined by your acceleration. And so depending how straight or how curvy your motion is, determines a lot about how much, where you're going to end up. So concavity is a numerical value that tells me how much I'm bending. So in this graph, we can take the first derivative and determine where the graph, or where the function is increasing and decreasing by whether the derivative is positive or negative. We then can take a second derivative to determine which way the graph bends. So I'm going to give you 4 possibilities, okay? There's 4 separate graphs I'm going to look at. This is going up, but bending this way. This is going down, but bending this way. This is going up, bending this way. This is going down, bending this way. These are the only 4 shapes any graph can have if it's not a line. Doesn't matter what the graph is. Every graph has got to be one of those 4 if it's not a line. You with me? For a portion of the graph. So, you see this over there? Yeah, it's the first one. How about this one? It's the third one. Every graph is going to have one of these pieces in it. What can you tell me about this graph? You can tell me that the first derivative is positive because it's going uphill. Can you tell me about the second derivative?
Negative.
It's negative because it's concave down. In other words, if I thought about it, if I kept going forever, I'd be doing that eventually. How about this one? First derivative is
Negative.
negative because it's going downhill. The second derivative is positive because it's bending upwards. Ooh, totally different. This one, the first derivative is
Positive.
positive because it's going uphill. The
And
second
positive.
derivative is positive because it's bending upwards. Well, it only leaves one possibility now, doesn't it? This one, the first derivative is
Negative.
negative, and the second derivative is
Negative.
also negative. These are the four things. So if I told you I'm thinking of a graph and the graph is increasing, the graph is increasing. It could be this, or it could be this, and those are very different shapes, aren't they? Because this one's speeding up, this one's really slowing down. If I'm thinking of a graph and the graph is decreasing, could be this, could be this. I cannot know which of those two shapes it is without doing the second derivative. Okay, so that's what we're going to do. We're going to use the second derivative. But we're also going to be able to use the second derivative to help us determine when we have extrema. We did a first derivative test last day, and that worked out really nicely. Okay, so I'm going to do a similar problem. I don't remember exactly what problems we did last day, so I'll make one up. Okay. So let's consider, I'll fix it in a moment. And I'll probably put this on Desmos later anyway. I want to think about this graph here, and we're going to do a lot of the stuff we did before. What we want to do is describe everything about this graph. We want to talk about critical values. We want to talk about intervals of increasing, decreasing. We want to talk about extrema. But we also want to talk about intervals of concavity. We want to talk about, does it have any inflection points? Now, this one should be relatively friendly. All right, so let's start with the first derivative. What's the first derivative here?
6x squared minus 6x.
Okay, I need to set that equal to 0, so let's factor it first. Does that factor?
Yes. X plus 1, x minus 2.
Beautiful. Okay. In calculus, we usually have things that factor very nicely. In reality, not so much. Okay, where will this be 0?
-1 and 2.
When x is -1 or x equals 2. So I have two critical values, which means I not only have two horizontal tangents, but I have two places where I can turn around. Does it mean I'm going to turn around there? No, but those are the only two places I can turn around. We understand that. Okay, so let's do our first derivative test like we did last day. So that's where I make my f prime number line. I put these numbers down. I've partitioned the number line into 3 intervals. Let's pick a number in each interval. So if I pick negative bazillion, I'm going to be negative, and that product is positive. If I pick a number between -1 and +2, how about 0? I am positive, negative, so that product is negative. If I pick a number positive bazillion, I'm positive, positive, positive. Okay, beautiful. So f is increasing in what interval or intervals?
Negative 40.
Beautiful. And always open intervals. These cannot be closed. F is decreasing.
-1 and 2.
Will I have any extrema? Extrema means a maximum or a minimum. Will I have any extrema? Yes or no? Yes. Cece's drawing it with her finger. Yes or no?
Local extrema.
Well, local or absolute we'll worry about last, but do I have any extrema? Does it
Yes.
change direction?
Yes.
Exactly how many times?
Twice.
How do you know that? It's that simple. I went up, I was flat, I came down. I was down, I was flat, I went up. I change direction 2 times. Okay? If you're going from increasing to decreasing or decreasing to increasing, you're changing direction. Can you tell me the extrema then? All right, well, we need our calculators. F of -1 and F of 2, those will produce y values. I need y values. So if I put a -1 in there for x,
13.
How do you do that so fast?
so 13. And if I put a 2,
-14.
-14. Okay.
Got it.
I was going up, I was flat, I was coming down. Is this a max or a min?
Max.
It's max. So I'll put blank max. I was going down, I was flat, I came back up. It's a min. By the way, it has to be as easy as what I've just made it. I'm going like this. It has to be minimum. If you're making it harder than that, you might get the wrong conclusion. Now,
They're
local
both
or
local.
absolute there's no calculus. It's not possible in any capacity to use calculus to figure that out. That's impossible. You look at one thing and one thing only. What's the degree of the highest term? 3rd degree. As x grows without bound positively, which direction am I going? As x grows negatively, so what does that mean about your extrema? They're
Local.
both
Local.
local.
Oh my god, this is right.
That's it. If you did anything else, I'm going to give you an absolute money back guarantee. If you did anything else, then it's an absolute guess. Because anything else has nothing to do with the conclusion. The conclusion is, which way does this go? Does it go up forever? Does it go down forever? The answer was yes in both cases. So both of these end up being local. Tell me, what is the look of a polynomial that does have an absolute extrema? Probably, if it's a polynomial. Probably tell me something about the look of the polynomial that has,
An even number.
yeah, it probably needs an even exponent. Oh, so like an x squared has an absolute, but it could also go this way.
Yeah.
Yeah, if you're doing a polynomial, you probably need an even exponent to get absolute. Will you get 2 absolutes?
Maybe not.
Yeah, it's harder. It's harder to get 2 absolutes, an absolute max and a min. It's possible, but I'm probably happy with 1. All right, we've done everything we did the last couple classes. Now let's look at the second derivative. So, take the second derivative of that.
12x minus 6.
12x minus 6.
Which is 6.
Is that right?
Yeah.
X minus 2.
Now, does this ever equal 0? Yeah. It equals 0. When does this equal 0?
Half.
1/2.
Oh, you fucking.
When x is,
Half.
at x equals 1/2. Agreed? 12x minus 6 when x equals 1/2. So here's what we're going to do. We're going to make an f double prime number line, and the only number we care about is the 1/2. I don't care about 0. 0 is not important. So if I pick a number more negative than 1/2, like huge negative, then this will be
Negative.
negative. Big number?
Positive.
Positive. So how do I make my conclusion? F double prime. F of x is concave up. F of x is concave down. You're concave up where your second derivative is positive. You're concave down where your second derivative is negative. That's it. So where is it concave up? From 1/2 to infinity. Where is it down? To 1/2. Extrema can only occur where I change direction. That's how we knew I got a max and a min. If I had 2 in a row that were below or 2 in a row that were above, I would not have changed direction there. An inflection point can occur only where you change concavity. Do I change concavity at 1/2? Yes.
Yes.
Now, an inflection point is not a value. If I talked about I'm on a road, it's really steep, I can give you a numerical measure of steepness. I'm on this windy road. Here's the spot on the road where all the accidents occur. Or here's the spot on the road where I finally, have control of the wheel. That's not a value, that's an address. An inflection point is the only ordered pair you ever give when you're talking about graphing. Because it has no value. This is a height. I reach 13 units high. I reach negative 14 units low. These are heights. These are values. The inflection point, we have it cleverly hidden in the name. Point is what? 1/2 comma. Put a 1/2 in there for x.
You can get negative a half.
You got negative half?
I got negative a half.
You got negative half? Well, that was fast. That's the inflection point. That's the only ordered pair involved in this problem at all.
And for when we're writing the concave up, concave down, is it okay if we write CCU, CCD for that?
Yeah.
CC?
Yeah, that's the shorthand we use.
Oh, that's one word.
Okay.
Yeah.
I was just wondering.
As long as you know what you're saying.
Okay.
I usually bring like con,
Okay.
con up, con down. Now, what does that mean in terms of my graph? Well, let's bring it up, shall we? Yes, I can freehand this, but I can do a way more accurate graph this way. Got everything written down, I hope? Okay. Okay, just so the recording is capturing every sound you are making, so probably you don't want to be goofing around the whole time. I'm not joking, I'm serious. We have it set to get all of your sounds so that your questions are captured for all eternity. That sounds pretty scary, huh? Okay. All right. 1 equals 2x cubed minus
3x squared.
What did I write?
You wrote 3x.
Oh, thank you. Thought I wrote. Oh, you know what?
Exponent on an exponent?
I know what it is. I did exponent twice. Hold on.
Yeah. Sounds good.
There we go. Okay. Yeah. There we go. All right.
Minus.
And then it was 12x plus 6. Yeah.
Plus 6.
I probably shouldn't write everything behind me, huh? All right. So this is kind of huge. So I want to change the x scale because everything that's happening is happening fairly tight. Wouldn't you agree?
Yes.
So maybe we'll go from, I don't know, like -5 to 5. That might be more worthwhile. Okay, that's pretty good. That's probably all we need. Now, you said that f of -1 is 13. Do you see it? Right there. Because that's -1 unit, 13 units high. Life is good. F of, what was the second one? F of 2 was -14. Beautiful. But what's happening, where's my inflection point? You said 1/2, comma, -1/2. Is that right? I don't think. Is it -1/2?
Yeah.
Did somebody double check, just make sure the calculation. If I put a 1/2 in there for x, doesn't feel like we're going to get -1/2. That's one thing. That's going. I think that's slightly off because that should be right here.
No,
Yeah, I got -1/2.
it's because the y-axis is in 5. Yeah.
Oh, thank you. You're right. Oh, good catch. Yes, he's absolutely correct. Because I'm counting, so -1/2 would be right. Yes, that's perfect. Now, if I cover up, you see this graph right here. This is absolutely concave down. Do you agree?
Yes.
Forever in that direction, it is concave down. There is no question whatsoever. But when I'm looking at this way, everything on that side forever is concave up. But at that point right there, I changed from down to up. If I'm on a windy road, that's the place where my steering wheel was straight for just a brief moment. That's why it's called an inflection point. I changed from bending. Use the windy road example. You're bending in one direction, you're bending in the other direction. For one moment, you're not bending. If I'm running, I'm speeding up, I'm slowing down. For one moment, I'm doing neither. That's what it means to be an inflection point. If you're talking about motion, it's where your acceleration is 0. Acceleration of 0 does not mean you're not moving. It means you're not speeding up or slowing down. You're in cruise control in the car. So if I'm talking about motion, it could be like I'm on a straightaway. I'm neither bending left or nor right for a while. So this is a wonderful example of being able to see how the second derivative works. Now, there's something also extremely powerful about the second derivative that we're going to use. This is called the first derivative test. I used the first derivative and where it was changing direction and all that to determine max and min. Can I do the same thing with the second derivative with completely ignoring everything I said for first derivative? Actually, you can. This is called, we have a really clever name, the second derivative test. Okay, good. You got me on that one. All right. The second derivative test. I want you to take the second derivative and evaluate it at both critical numbers. So I'm going to evaluate the second derivative at -1 and at +2. Now, remember what my second derivative was. I've erased it. It's 12x minus 6.
Yeah.
So what is the second derivative if I evaluate it at -1?
Negative 18.
It's -18. At 2?
18.
Positive 18. It's not the value, it's the sign. The second derivative tells you about the bend. Now think about it, it's real simple terms. I have a horizontal tangent and my curve is bending up. I have a horizontal tangent and my curve is bending up. Wouldn't that have to be a minimum?
Yes.
I have a horizontal tangent and my curve is bending down. Wouldn't that have to be a maximum?
Yes.
The second derivative test is exactly that. If I take my critical values, I plug them into the second derivative, I'm not going to get 0. No, I'm going to get a positive or a negative number. If I get a positive number, it means I'm concave up where there's a horizontal tangent. That means that it's a minimum. Is that the conclusion we got over there, by the way?
Yeah.
Yes. I'm concave down at a critical value. So that means it's a max. You notice I only tested the critical values. So it turns out when I'm trying to determine if something's a maximum or a minimum, the second derivative test is often simpler than the first derivative test. Because the second derivative, if I'm dealing with a polynomial, doesn't each derivative get simpler? Because it's of degree less. So the algebra required to answer a question gets easier. So a lot of folks would say, no, I'm going to use the second derivative test every time. But if your function is somewhat complicated and each derivative is more work because you have chain rules and product rules and quotient rules, then the second derivative test is absolutely going to be harder. The beauty is the first derivative test and the second derivative test always yield the exact same conclusion.
I have 2 questions.
Yes.
One, how would you use the second derivative test to draw a sketch of the graph?
No, you're not doing it you're just testing the critical value to determine max and min.
Okay.
What we did right here, I slightly erased it. We got this answer right here, local max, local min,
Right.
from the first derivative test by looking at my shading, right? Increasing, decreasing. But now that I have my critical values, if I plug them into the second derivative is either going to be positive or it's going to be negative. Think of it like this. Doesn't this say I'm going like this?
Yes.
Which means I'm also concave down there. Aren't I going like this? Yeah, which means I'm also concave up there, and that's what that said. So you actually have 2 viable options to determine a max or min. You wouldn't do both of them because you wouldn't need to. You got your answer here, you're there. And I'm going to show you as we do more and more problems, there are going to be times when I say, well, let's find the max and min, you did the first derivative, you go, you know what, I'm going to use the second derivative test because it's going to be easier algebra. Because the first derivative test, I have to determine each interval is increasing and decreasing. That can be a little bit of work. If my function is complicated enough that an additional derivative will be more work, and we're going to look at that too, then I'd probably go first derivative test. Okay? But you actually always have an option, and you always get the same answer.
And the second second question, are trig functions the only times where we have absolute maximums and mins?
Not
At the same
necessarily.
time?
Well, I mean, think of something as simple as a parabola. An upwards opening parabola is going to have an absolute min.
No, I mean like since, like both a maximum.
Oh, at the same time.
Yeah, at the same time.
No, that actually comes from our second part of class today. If I have a graph that has asymptotes, particularly like horizontal asymptotes. By the way, that's a great question. Remember the inverse tan had two horizontal asymptotes, so it kind of looked like a sideways version of the tangent. Well, what if I did it with the inverse sine? I now actually have an absolute max and an absolute min because they're going to be endpoints. It has to be a little more complicated, but I can have an absolute max and an absolute min, but it's not going to be a polynomial. It's never going to be a polynomial because I'm always going to have something go off to infinity there. But that is a great question. It's probably a more complicated graph to begin with in order to have that happen. We study things like this at the higher levels where I have two horizontal asymptotes, for example. So my maximum would be only reached by a limit, and my lower would be by a limit. That's called logistic growth. We do problems like that. That's very similar to the inverse tan function. I had the same thing happen. I had a high and a low, but I never quite reached them, pi over 2 and negative pi over 2. So for right now, the second derivative tells us about the bend of a graph, concavity. Now, it's an inflection point only if I change concavity. Okay? A critical value is where my derivative is 0, or the derivative did not exist, but the function did. Remember? So there was the weird one. So let's consider a few different graphs here. Let's start with y equals x cubed. We did this one, I think, last day. This equals 0 and x equals 0. I have exactly one critical value. So when I make my I'll call it the f prime number line, just to be lazy. I only have one value. But what's goofy about this one? I'm positive on both sides, aren't I? So we say that f is increasing from negative infinity to 0, and then again from 0 to infinity, and it's never decreasing. Does the function change direction? No. We have a good idea what the function looks like, but it does confuse us a little bit. But that's because we didn't have the second derivative yet. Now let's consider the second derivative. What's the second derivative?
6x.
6x, and that does equal 0 at x equals 0 also. But something interesting is happening there that didn't happen in the first derivative. I change concavity at 0, don't I?
Mm-hmm.
Okay, so f is concave down from negative infinity to 0, and f is concave up from 0 to infinity. I changed concavity at 0. That means I have an inflection point. And where's my inflection point? Is where? It's at the origin. Now, does that help explain what the graph looks like? What do we know about the graph of y equals x cubed? I'll put it over here. It has a horizontal tangent. We know that. That's y equals x cubed. To the left, it's concave down. To the right, it's concave up. And I have a horizontal tangent here. Do I have an extremum? Is there a maximum or a minimum? No. But I do have an inflection point. And that helps explain why that one was so awkward. We said, wait a minute, shouldn't I have a max or a min at, at the origin? No, I changed concavity at the origin. You with me? So it's an inflection point at the origin because I changed concavity there. That's the place on the road where I went from turning the steering wheel to the right to turning it to the left, if you will. Okay? It's that brief moment in time I wasn't turning my steering wheel at all. Now let's look at a couple of the other ones we've considered recently. Okay, one of my personal favorites. I'll write it as f of x this time. X to the 2/3. Okay, we've worked with this one a couple of times. So 2/3 x to the negative 1/3, which is 2 over 3x to the 1/3. Now, does this ever equal 0? No, because I have an x in the bottom. My domain, we know, is all real numbers. I can raise it, any real number to the 2/3 power. That's not an issue. There's no imaginary numbers going on there. But this is undefined at x equals 0, is it not? So something interesting is happening at x equals 0. Now, my first derivative test. Okay, if I take a large negative number, this is going to be negative. If I take any positive number, this is going to be positive. So I can say f is increasing from 0 to infinity. F is decreasing from negative infinity to 0, correct? Do I change direction at the origin? I went from decreasing, something weird happened, and then I was increasing. Did I change direction? I went from going down to going up. Did I change direction?
Yeah.
Yes. Is it a horizontal tangent? No. What was it? Do you remember? It's a cusp. We now know what that point looks like, but the graph itself I'm decreasing, something weird happened, I'm increasing. So we know then, based on the first derivative test, we know that f of 0, which equals 0, is the absolute minimum, don't we? Okay? Now let's consider the second derivative. Because this one's going to be a little bit weird. So my second derivative, I'll put up here. What's the second derivative?
Negative 2/9 times,
Yeah. Negative 2/9
times x to the negative 4/3.
x to the negative 4/3, which is negative 2 over 9 x to the 4/3. X to the 4/3. Is that ever negative? That exponent of 4. X to the 4/3 is never negative, is it? So tell me about this whole thing. Because it's a negative in front, this thing is always negative, isn't it? Because of the negative in front, that's always a negative value. So if I do my f double prime number line, by the way, this is not defined at x equals 0. Do you agree? So should I include x equals 0 on my number line? Yeah, just like I did with my first derivative. I should definitely include 0. Now, to the left, it's always negative. To the right, it's always negative. Did not change concavity. So in simple English, without the benefit of a graph, pretend we never drew the graph. I know that's going to be hard, but pretend this is not there. Can you say that f is concave down, basically almost the entire number line?
Mm-hmm.
Now let's look at our graph. Down, down. It's always concave down, isn't it? For the whole duration of the graph. So is the origin an inflection point? Something interesting was happening at the origin. In fact, we got an absolute minimum there. Is the origin an inflection point?
No.
No, because
Concavity didn't change.
I did not change concavity. So what you're going to find is, in the y equal x cubed, the origin, I did not have a maximum or a minimum there, but I did have an inflection point. Over here, I had a maximum or a minimum, but I did not have an inflection point, even though 0 showed up in both. A place on the graph cannot produce both an extrema and an inflection point at the same time. That's not possible. You can't change concavity and be a max or a min at that same place. That's not possible. You could be one or the other, but you cannot be both. And I just gave you examples where you were one, you were the other, but you were not both. Now there's one more I want to do. One more weird one. The cube root function. prime is 1/3 x to the negative 2/3, which is 1/3x to the positive 2/3. That is always positive, because x to the 2/3 is never negative. So we know that f is, f is increasing from negative infinity to 0, and then again from 0 to infinity. I am undefined at 0, just like before, but I never change direction, do I? Okay, so on my f prime number line, if you will, I'm that. It's always going uphill. There's a blip at 0, and then I'm going uphill again. Now let's consider the second derivative. Let's differentiate that one there.
Negative 2/9 times x to the negative 5/3.
This is not always positive or always negative because I have an odd exponent on the x, so it's going to change signs. So let's do our f double prime number line. So if I take a large negative value, then x to the 5/3 would be negative. But I have a negative here, so that means it's positive. If I take a large positive value, then x to the 5/3 is positive, but I have a negative. So f is concave up from negative infinity to 0. F is concave down from 0 to infinity. Do I change concavity at the origin here?
Yep.
Yes, and I am defined at the origin. The derivatives aren't defined there, but the function is. So do I have an inflection point?
Yes.
Yes. Where? Inflection point at 0, 0. Now, this is also a very interesting graph. I'm going to graph it over here. And let's see if it agrees with everything we just said. It's basically the inverse of that one over there, isn't it? What's happening at the origin? I have a vertical tangent. Remember I said you couldn't ride your bike up this hill. You know, you'd go straight up and come crashing down. Now, do I ever change direction? No. But tell me to the left, aren't I concave up?
Mm-hmm.
And how about on the right?
Concave
I'm
down.
concave down. That's what that said there, and I have an inflection point at the origin. So the calculus gave us all the answers, and then I drew the graph after the fact. Yeah.
For the inflection point, do you plug in the value into the second derivative or the original?
Well, to find the point, you need the original function. Yeah, you always use the original function to find the point. So in each of these cases, we have graphs where weird stuff's going on. Remember, we talked about the evil cool numbers, the ones where it's not defined, but the original function was. So I can have derivatives where, you know, I get stuff in the denominator, doesn't work, but the original function was fine. So they're the other kind of critical values. And so we just did several of the examples, right? One was a cusp, one produced a vertical tangent, and so on. Okay, you with me on that? So let's look at a graph that we looked at last day, actually the last 2 days, because we haven't looked at the second derivative of this one yet. I like reusing things. I think this was what it was. Now we did the first derivative, we graphed it on the first day. Then we used the first derivative test last day and we did all the work. Now I want to look at all the second derivative information because we have not been able to see that quite yet. So if I distribute, by the way, are there any domain restrictions?
No.
No, that is important. Okay, that is very important. If I have domain restrictions, again, it can affect all of the other things that I come up with. So I have 5/3 x to the 2/3 minus 10/3 x to the negative third. I'll remind you what we did. We factored out the common factor, and that left us with x minus 2. So I rewrote that as 5x minus 2 over 3 times x to the positive third. This is 0 at x equals 2. And what else? It's undefined at x equals 0. So I have two really important critical values. Again, we've done all this before, but we're going to piggyback on this. So, hugely negative, we'd be negative over negative. If I use x value of 1, then I'm negative over positive. If I use an x value bigger than 2, then I'm positive over positive. Great. So we said f is increasing negative infinity to 0 and 2 to infinity. F is decreasing 0 to 2. And because of that behavior right there, how many extrema am I going to have? 2, because I changed direction 2 times there. So we can say with certainty f of 0 which equals 0 and f of 2 which equals negative 3 times the cube root of 4, whatever that is. This is a blank max or min? Max. Min. Now I go back to here and say, as x grows without bound positively, this is going to be positive, so there's no absolute max, it's got to be local. We're going to pretend like we haven't drawn this picture yet. As x grows negatively without bound, this is going to be positive times negative, which is negative, so they're both local. Okay. Now, we did draw the graph. Not worried about the graph. Now I want to talk about the second derivative. Which do I want to differentiate? Do I want to differentiate this form?
No, the first thing you do.
This one?
Up on
This one. Yeah. Never differentiate the factored form. It's way more work. You all understand that? We didn't differentiate this. We multiplied it out, then we differentiated. The factored form is to graph with, to plot points, to figure out where it's 0. But when I differentiate, no, I want to differentiate that, and I want to differentiate that. Just way easier. So, let's use blue this time. What is my second derivative going to be?
10 ninths times x to the negative 4/3. Negative 1/3.
Times
sorry.
x to the negative 1/3.
Plus 10 ninths times x to the negative 4/3.
And by the way, you notice these differ by 1, these differ by 1. All my exponents are going to differ by 1. That makes the factoring a little bit easier. So 10 ninths x to the negative 4/3, and what does that leave?
X plus 1.
X plus 1. Beautiful. So this will equal 0 at x equals negative 1, and of course it's undefined at x equals 0. All right? I'm going to let me do this for a moment. We're going to come back to this. I need the space. So now let's do our second derivative test. So I make the second derivative number line first to figure out the intervals of concavity, and I need negative 1 and 0 both on there. Now, let me go ahead and finish writing this one in a way that's easier to work with. X to the 4/3 is always positive, isn't it?
Mm-hmm.
But the top is definitely going to change signs. So if I take hugely negative number, then I'm negative over positive. If I take small negative number, then if I'm between negative 1 and 0, then that's positive, isn't it? Like negative a half. Positive over positive. Ah. Now, if I take any positive number, it's, again, positive over positive. Do I change concavity?
Yes, at negative 1.
How many times?
Once.
Just once. Okay? So, F is concave up, F is concave down. I'm up negative 1 to 0, and then again 0 to infinity. I'm down negative infinity to negative 1. I change concavity at negative 1, so I will have an inflection point. This is where I give the ordered pair. So inflection point at negative 1 comma Now here's where I'd go back to the first one. Negative 1 to the 2/3 is 1. Negative 1 minus 5 is negative 6. Do we agree? So I have an inflection point there. That's where the graph's going to change the bend from up to down or down to up, depending which way you're looking at it. I do not change concavity at x equals 0, but notice I had a maximum. Oh, I said you can't have both. You can't have an extrema and an inflection point at the same place. So we had an extrema, but not an inflection point. You notice I don't have an extrema when x is negative 1, do I? Okay, so far so good? So we've answered everything we can say about this graph from this standpoint. Now we'd like to see what does it look like graphically. Down again. It'll change every moment, so. Whoa, 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 whoa. I need to get out of there. Sorry. There we go. Whew. Okay, sorry. I don't know if you guys can see that. I didn't get out of the exponent and it came out pretty crazy. Okay, now it's good thing you can see that. All right, now let me change my picture a bit. We make x. What did we do before? I think we didn't need quite that much, maybe about negative 2 to, I'll go to 10. And then I'll make y. No, maybe go a little bit more. I'll go negative, maybe negative 5 to 10. Okay, can we see enough there?
Yeah.
So we see our, at 2, this is not quite negative 5. If you do this on the calculator, what is negative 3 times the cube root of 4? It's about what? Oops. Yeah. There we go. It's about 4.76. So that's about a y value of about negative 4.76. It's not quite negative 5, but that's where my minimum occurred. It's a local min. That's a local max because that goes up forever. But here's the crazy part. Negative 1, I'm right here. It is so subtle that the naked eye can't even see it. But it changes concavity there. How do I know? Where's my concavity? I am concave up from negative 1 to here, and then the rest of the way. It's really hard to tell, but this is bending slightly upwards. I'll zoom in a little more. But right now it's bending slightly upwards, and then it's bending upwards the rest of the way. But from here it's bending slightly downwards. It is really hard to tell, so let me squish it a little bit more. And let me go negative 2 to, I'm going to just do this much of the graph. Whoops, hold on. No, that's not, okay, hold on, let me go the other way. Let me go negative 20. Still not sure you can see it. Can you see it? It's bending. It's almost impossible to see. It's bending slightly, because you can see the little bend right at the end there. It's bending slightly up here, and can everyone see just a little bit of the bend there? It's so subtle that the naked eye would not have caught that. But when I did the calculus says that's where the bend changes, and the bend stays forevermore because we have it as intervals. This one is a little tricky in that manner, okay? So we've looked at multiple different examples today. Now the second derivative will help us with the shape because it gives us more information rather than just putting an arrow, right? Which way does it bend, that sort of thing. Now, one thing we haven't done in this problem is use the second derivative test to determine whether I had a max or a min. We used the first derivative test. Let's use the second derivative test. So here's my second derivative. I'll use this form right here. What is f double prime of 2? If I put it in here. It's 10 times 3
Positive.
over 9 times 2 to the 4/3. It's positive. That's all we really care about. And what does that tell us? It's concave up where there's a horizontal tangent. Does that mean it's a min?
Mm-hmm.
Yeah, it's this guy right here. Can I use the second derivative test on the other critical value? Can I use it on 0? No, because it's not defined at 0. Oh, so the second derivative test in this case didn't work for both of them because it wasn't defined at 0. The first derivative test told us that something was happening at 0, right? Because I changed direction. Even though the derivative didn't exist at 0, I could show it changed direction at 0. But the second derivative test I cannot evaluate at 0 because the second derivative, again, is not defined at 0. So in this case, the second derivative test failed us for one number, but it completely confirmed the other one. Everybody cool with that? Okay, we're going to stop in a moment. I'll do the roll. When we come back, we're going to look at the asymptotic behavior of graphs and some of the coolest things we haven't considered yet, but it's sort of to round out the picture. We have the first derivative test, we have the second derivative test, but many of the graphs we deal with have asymptotes. Think logs, think exponential functions, think polynomials, right? Same degree, that kind of stuff. Okay, go ahead and stop that. Okay, we're now going to look at asymptotes and asymptotic behavior again, but now from a graphing standpoint that we can figure out what something looks like. So the first thing I want to do is, how do you actually identify asymptotes? So let's take something we already know fairly well. So we've got y equals 3x squared minus 4x plus 1 over 5x squared plus 2. Yes, I can take derivatives, I can set things equal to 0 and all that. I'm not interested in that right now. I'm just interested, is there any asymptotic behavior of this? Well, what would be the limit as x goes to infinity of this y function?
3 over 5.
3 over 5. So what does that mean to you? What exactly does that mean?
That at x equals 3 over 5.
That means when I'm out here, I'm either going to go this way or this way. I'm either going to go this way or this way. I don't know which side I'm on. But it means that the graph becomes indistinguishable from the horizontal line at some point. Because if the limit is a constant, then that means my y values are approaching a constant. Now we can multiply top and bottom by 1 over x squared and then consider transient terms. Or we can take the easy way out and just say same degree. Okay? So when you have a rational function that's the same degree, we will always get a horizontal asymptote, and we know how to find it. What if, let's do a different one, y equals, I'll do the same numerator, and I'll do almost the same denominator. What is this limit?
Yeah.
This one's going to be 0, isn't it? What does that mean? That means the x-axis, the line y equals 0, will serve as an asymptote. Kind of like in an exponential function, we see that. So in both cases, I have a horizontal asymptote. One of them was y equal a constant, the other was y equals 0. But a horizontal asymptote is usually fairly simple because I can look at just the degrees. Now, if I throw in other things, exponential functions, logarithmic, yeah, it's a little bit more difficult. But certainly for rational functions. Now, what if the numerator has a higher degree than the denominator?
Maybe.
Can I still have asymptotic behavior? Yes, we did this before. And this was the one we did. I've shown you this one. Remember, we had all sorts of weird stuff, but when we did the long division, we got this. So we said this function here is asymptotic to x squared. So the correct way of saying it is, because if I graph this, and we did this, and then if I graph y equal x squared, we won't be able to distinguish the difference. This is asymptotic behavior, but this is not an asymptote. An asymptote is a line. Asymptotic behavior just means, one acts like the other. But what we're interested in today is not this problem, but things that produce asymptotes. So in this case here, I don't have an asymptote. So let me throw a what if at you. What if I make the problem y equals, let's say, x cubed over x squared minus 1. Well, obviously if I take a limit, right? If I take a limit, the numerator has a higher degree than the denominator. So if I take a limit as x goes to infinity, I know it'd be infinity. We know that. But that degree difference of 1, what if I did the long division on this one? I did it on that one. So let's do the long division. You guys remember how to do this? Got to put all the missing terms, right? So, how many times does x squared go into x cubed? Goes in x times, and then when I multiply, I get x cubed minus x. I'm going to subtract those quantities, and then on the next line, what do I get? 0, 0, x, and that's it. 0, 0, and you're making faces. This is not something we should struggle with.
Oh, no, I'm just blind right now, sorry.
That's all I got left. Now, am I done? Yeah, why? Because that's a smaller degree than that. Oh, okay. So what does this equal? X plus x over x squared minus 1. And if I put them all together, I'd get the same thing. Remember, you're done when your numerator is a smaller degree. Now, this is a very interesting thing. This function, because it equals this, we said it's asymptotic to this because that's a transient term. If it helps, can I think of this, not that I would want to do this in general, but can I think of this term here as 1 over x minus 1 over x, if I had to? In other words, is this a transient term also? Yeah. As x gets big, this is getting really small really fast. So does that mean this is asymptotic to x? Yeah, that's exactly what it means. So let's do that. Let's draw both of these on the same set of axes. There are 3 types of asymptotes, but this is the one that most people don't think about. They don't consider x cubed over x squared minus 1. It's probably the most interesting one too. Oops, sorry, I don't need parentheses. X cubed. There we go. Okay. Now, this is. Okay, I think we can officially say this looks like crazy math, right? This looks completely out of control. Look at all this behavior. Look at all this weird stuff going on. Now, I want you guys to back up. And I want you to keep backing up. I want you to keep getting farther and farther and farther. Let me change the x and y so they're the same. Hold on. Let me make that, how about negative 100, positive 100, negative. I want these to be the same so my scales aren't so whacked here. And okay, I just want negative 100 to 100 in both directions. Do you notice anything about your graph? See that diagonal line? No. Keep backing up, keep backing up, keep backing up, keep backing up. Anybody notice anything? What's the only thing you see? You see the line y equal x, don't you? Does everyone see that's the only thing you see? That's the line y equal x. But way up close it doesn't look like that, but asymptotic behavior is what's happening when I go that way forever. Okay, so let me zoom in closer and closer. Yeah, interesting stuff is happening. But the graph itself, as x gets bigger and bigger and bigger positively or negatively, the graph is acting like y equal x. So does that make y equal x an asymptote in this case? Now remember in the previous one, we're going to be going back and forth with this. This is asymptotic behavior. That's not a line, so it's not an asymptote. This graph looks like a parabola when I step back. But I said this graph looks like this line when I step back. So is this an asymptote? Yes. This is an asymptote because it's a line. It has a name. It's called an oblique or what I like, slant asymptote. Everybody here is familiar with horizontal asymptotes, and actually we're pretty familiar with vertical asymptotes, right? That's where the denominator is going to be 0. But a slant asymptote is just as important as those two, like in this last graph. It seems kind of weird, I know, but this graph right here, this crazy thing right here, actually thinks it's this line. Because if I replace x with larger and larger and larger values, I'm not going to see much difference. If I got out my calculator and replace x with 1,000, okay, just for fun, put 1,000 in there. 1,000 cubed divided by 1,000 squared minus 1. My calculator says the answer is 1,000.001. It's pretty close to 1,000, isn't it? If I do it with a million, my calculator will say it's exactly a million, although it isn't, because of calculator deficiencies. The larger value I put in for x, the more likely I'm going to get the exact same value back again. This function thinks it's the line y equal x. Because as x gets big, these become indistinguishable. Okay, because of the transient term. That makes that asymptote very, very interesting. Now, I've shown you the ways to get horizontal. I've shown you the ways to get a slant. Where do vertical asymptotes come from?
Yeah. Restrictions underneath the quotient.
Are there any discontinuities in this graph?
Yeah.
The numerator is not 0, but the denominator is 0 where?
At 2 and -2.
So the vertical lines x equal 2, x equal negative 2, these are vertical asymptotes. A vertical asymptote is not even like a removable discontinuity. A vertical asymptote is when the denominator is 0 and the numerator is not. By the way, have we done this already? Yeah, you guys identified this on the first test. You identified where vertical asymptotes can occur. So the easy asymptotes are usually the vertical asymptotes because the denominator is 0 and the numerator is not. The horizontal, if I have a rational function, I'm just looking at degree. Same degree, I get a constant, y equal a constant. The numerators of smaller degree, y equals 0. The tricky one is the slant. You're going to see a slant asymptote when you have a rational function. This is a rational function, but the degree difference is exactly 1. The numerator is exactly 1 higher than the denominator. So when I do the long division, I will see a line plus transient term. And we're going to look at that one also today. That's probably the most interesting because it's the one that we have the least experience with. Okay? So, let me ask you a question. Tell me where the following graph will have asymptotes. How about y equals 2x squared minus 3x plus 9 over x squared minus 9. The numerator does not factor. I'm just making that easier.
Are you asking for the vertical?
Will this have any asymptotes?
Yeah.
Minus 3 plus 3.
It's going to have exactly 3. All right, so the first thing I would do is I go like this. All right. Does it have any vertical asymptotes?
Yes.
I'll abbreviate. Vert asymptote. Remember, asymptotes are not numbers. They are lines. So I'll have people say, well, the asymptotes are at 3, 5, 7, and 9. I don't even know what that means. X equal 3, y equal 3. I mean, yeah, a number can't be an asymptote. A number is just a point on a number line. So vertical asymptotes are always x equals. So what are my vertical asymptotes?
X equals 3, x equals -3.
All right. Same degree?
Yes.
Am I going to get a horizontal asymptote?
Yes.
The way you get a horizontal asymptote is by taking the limit as x goes to infinity. I don't need you to take the limit as x goes to infinity because you already know what it's going to be. What will be that limit?
2.
Positive 2. So my horizontal asymptote is the line y equals 2. That's all I got to say. And how did I come up with that? Because if I take the limit to infinity, I'm going to get 2. So that means the horizontal line y equal 2 is what this looks like. So if I do this one on Desmos, I'm going to see all sorts of crazy behavior. Let's do this one on Desmos. Back in the day, I had to do all these by hand. I love those moves, because I'm not that good at drawing. Okay, good. All right. See all sorts of cool behavior here? It's, oh, you can't see the cool behavior. You know, okay, just take my word for it. It's really cool. Sorry.
Wow.
Wowzers.
We're gonna, all right. Probably shouldn't turn it off. It's taking forever to reboot every time. There we go.
Wow. Wow.
Cheapers, Batman, right? Okay, can you see the vertical asymptotes? You're never going to have dotted lines. You see the vertical asymptotes? See, it's right here. There's x equal positive 3. There's x equal negative 3. It's hard to see because you don't see the dotted lines, but can you see where the graphs are not quite hitting those vertical lines? Let me back out a little more on this. Right, you see those? Oh, actually, I'm covering it up there. There's the 3, the negative 3, there's the positive 3. Now, see this guy right here? As x gets bigger and bigger and bigger and bigger, that's looking like a horizontal line, isn't it?
Yeah.
And it's a horizontal line, if you look, 2 units high. You see it? 2 units high forever and ever and ever. So you can see clearly the vertical and horizontal asymptotes. Did you need the graph to find those?
No.
No. God, no, you don't have to draw the graph to find them. So you found the vertical by setting the denominator equal to 0. You found the horizontal by taking the limit. You're not setting the numerator equal to 0 ever. That would only tell you the x-intercepts. That's not in any way helpful for what we're doing here. Okay, so that's that one. Let's consider now the following graph. Erase this. We want to do everything calculaic for the following graph. Okay. Will this graph have asymptotes?
Yes.
How many?
No, 3.
3.
I'll have 2 vertical and 1 horizontal. What will the horizontal asymptote be, by the way?
0.
Y equals 0 because of the degrees. That I need you to know without doing any work. That's where you get to use the degree argument because it's a rational function. There's nothing clever you have to do. If you want to multiply top and bottom by 1 over x squared to convince yourself, or just say, look, numerator smaller than denominator, I'm going to have y equals 0 show up as a horizontal asymptote because the limit of the function is in fact 0. And I have 2 verticals. So let's identify them first of all. I'm going to be lazy. Vertical asymptotes are where?
X equals 2 and x equals negative 2.
X equal 2 and x equal negative 2. My horizontal asymptote?
Y equals 0.
Y equals 0. Will this help me draw an accurate graph? Yeah. We're going to do this. We're going to plot 1 point on this graph. It does go through the origin. I'm going to take advantage of that. And I'm going to be able to draw you an incredibly accurate graph without plotting any points. Only using derivative information and the asymptotes. This is what I want to be able to do. So let's start with the derivative. Straight up quotient rule. So bottom times derivative of top minus top times derivative of bottom over the square of the bottom. Agreed? Now, can I clean that up a bit? That's negative 2x squared, so this is going to be negative x squared minus 4 over x squared minus 4 quantity squared. Is that numerator ever going to equal 0?
No. Wait, the numerator? No.
If it helps you, could I write it like this? Would that be legal to write it like that?
Yes.
Yeah, just for the purposes of being able to see, oh, my numerator is the sum of squares. It's never 0. Agreed?
Yeah.
The bottom is being squared. Can I actually say this? That is always going to be negative for every value I can possibly use? Yeah. Is that going to be useful? Yeah, that makes it really easy to describe my f prime number line. On my f prime number line, I do have a couple of breaks. What are they? Negative 2 and 2. Because it's not defined there. Where you are not defined, you can potentially change sign. We saw that in the earlier examples we did. So, to the left, I'm negative. In between, I'm negative. To the right, I'm negative. That's what we just said. This function, think of it this way. It's like an Escher drawing. It's always going downhill, forever and ever and ever. Even with asymptotes, this is always going downhill. That seems kind of odd, doesn't it? So we can say that f is decreasing from negative infinity to negative 2, from negative 2 to 2, oops, and from 2 to infinity. Do I have any critical values? Is the derivative ever equal to 0? No, that would be the denominator. No, is the derivative ever equal to 0?
No.
Remember, a quotient can only equal 0 where the numerator is 0, and you said the numerator is always negative. So I have no critical values, but I am decreasing everywhere, which seems really odd. Okay, let's now look at the second derivative. It's going to be a little more work. Now, because my denominator is being raised to a power, this is one of those I probably would be better off writing it as a product and doing product rule. If your denominator is being raised to a power, a product is always going to be easier than the quotient rule, and way less simplification. So let me erase that. Let me rewrite this as negative x squared minus 4 times x squared minus 4 to the negative 2. Now it'll be a little easier for me to take the second derivative. Okay, first times the derivative of the second, chain rule factor, plus the second times the derivative of the first. Okay. We can factor out an x squared minus 4 to the negative third, and that'll leave us with that term, that term, that term. So that's negative 4x times this. So that would be 4x cubed plus 16x. I'm factoring all but one of these out. So there's an x squared minus 4 left times negative 2x. Okay, did I mess that up, or is that okay? Oh, times negative 2x, sorry, cubed. Now, okay, so let's clean the inside. That looks like 2x cubed plus 24x. Is that right? Okay, all over this. This is my second derivative. Is this ever equal to 0? It turns out it is. It is going to be 0 somewhere. Can you factor that numerator? Let me erase this just for a second. I won't turn it off. Can I factor a 2x out of the numerator? Then I have an x squared plus 12. X squared plus 12 is never 0. But 2x is 0. Where is this 0? When x is 0. Oh, so I have one interesting value finally. Finally something cool happened. So this is going to be 0 when x is 0. Now what we need to do is make our f double prime number line. This is going to be a little bit tricky because I have 4 intervals. Big yikes. Okay? Take something hugely negative. Hugely negative. I'd have negative times positive over positive.
Negative.
Let's take negative 1. Positive, negative, 1 minus 4 is negative, so negative. So is that positive now? Yeah. How about we take positive 1? Positive, positive, negative. And finally, something hugely positive. Wow, I have all sorts of inflection points, don't I? Do I? I change concavity at 2 and negative 2, but those are vertical asymptotes, aren't they? Oh, I don't have any inflection points there, I just changed concavity there, but I also have 2 different pieces of the graph. Well, what about at 0? 0's in the domain, isn't it?
Yes.
So am I gonna have an inflection point there?
Yes.
Yes, finally. So this graph is gonna be concave up here and here. It's gonna be concave down here and here. And I'm going to have an inflection point at 0, 0. I am now going to draw you a perfect graph. And 0, 0 is the only point I'm going to put on my graph. It's the only point I'm going to bother plotting. I'll do it on to the right. This is where we use the understanding of the increasing, decreasing concavities. Now, if I want perfection in terms of exactly what points it passes through, then I just make a table of values. But I have technology at my side, so I don't even really need to do that. So what order do I do things? I put the asymptotes first. Clearly, you gotta use orange for that. So what are my asymptotes? X equal positive 2,
And negative 2.
X equal negative 2, and Y equal
0.
So, can you cross, technically, can you cross a horizontal asymptote? Actually, you can. We just don't see a lot of graphs do that. Yeah, you can cross a horizontal asymptote. It just says what's happening that way. Now, I'm not saying this one does. It does. But you can cross a horizontal asymptote. You cannot cross a vertical asymptote because you're not defined there. Now, there. We agree? That one's there. To the left of negative 2. This graph is decreasing and it's concave down. How can I be decreasing and concave down? I'm going downhill and I'm concave down. That's how I do it. I'm decreasing and I'm concave down and I'm not crossing the x-axis, so it has to be on this side. Again, how do I know that? Because we wrote it down. I'm decreasing. I'm concave down. Now, what about between here and here? Well, actually, let's do the other side. To the right of 2, I am decreasing, but I'm concave up. How do you do that without crossing? How do you do decreasing and concave up? Do you remember we talked about this before? Right? When the first derivative is one sign and the second derivative is another sign, I have one more section, the in between. Tell me what's happening in here. The first one says I'm completely decreasing, but the second one says I'm concave up until I get to the origin, then I'm concave down. How the heck could you do that? There, we're done. You like that?
No.
We plotted a lot of points. Well, your only other recourse is to literally plot 100 points and connect the dots and probably be all over the map. We started by putting down the asymptotes. They were our guidelines. I have to be approaching the asymptotes. By the way, did I cross a horizontal asymptote here? Yeah. But I crossed it here. I didn't cross it down there. So now, to get confirmation, I like getting confirmation.
That's gross.
It's gross.
No.
You're in a calculus class. Do you have to be able to do this?
Yeah.
Yeah, everything I did is actually something you have to be able to do at some point. But the cool part is there was nothing algebraically nasty about this one. Now, look at that. Kind of cool, huh? Is that what we just did? Yeah. Now, these derivatives weren't that fun because I had quotients, I had yucky stuff. But in this case, it wasn't the derivatives as much as getting the asymptotes correct. The asymptotes told me so much about what was going on there. Yeah, Susie.
So, how often do we come across functions where it crosses the horizontal asymptote? Not very often.
It depends what class you're in. Physics, 100% of the time.
Calculus.
Most of the time. Everything we did earlier when I talked about the horizontal asymptotes, it crossed the horizontal asymptote multiple times. Horizontal asymptote says what's happening that way, but I can do anything I want in between. Did I talk about harmonic motion in this class at all?
No.
Okay, we do that in Calc 3. Harmonic motion, I see. Think of bad shock absorbers.
Right.
You have a horizontal asymptote, hopefully you're leveling the car out, but you can cross it infinitely many times as your oscillation gets smaller. Good shock absorbers is you only cross it twice. Good shocks, you cross it twice. Bad shocks, you cross it a lot. Earthquakes. Yeah, anything with tremors that are getting lesser, you're crossing the horizontal asymptote technically as many as infinitely many times. If I took the sine of x and I divided by x, I'm going to cross the x-axis infinitely many times as I approach the x-axis. So that's not a concern. We only care about that. We're not. The concern in close was only because the graph didn't do a whole lot of different stuff in close. So we only had that middle part to concern ourselves with. Now, there's one more really, really cool but very important graph we're going to look at because we haven't looked at the slant asymptote yet, the oblique. I like using the word slant rather than oblique because it's clearer. It's the diagonal asymptote. And that's the one where you have a rational function, but very specifically, the degree of the numerator is exactly one more than the degree of the denominator. Which brings the question, can you have a slant asymptote and a horizontal asymptote at the same time? Well, that note was pretty quick.
I would say yes.
When would you have a horizontal? When the degree is the same or the numerator is smaller? When do you have a slant? When the numerator is exactly one more. So can you have horizontal and slant at the same time? No. You could have one or the other. It doesn't mean you're going to have both. Can you have either one of those together with a vertical? Yeah, we already did. Vertical is totally independent of the other guys. Okay? So let's consider the following. Let me just come up with something truly diabolical. Because I like diabolical. All right. I would like to, everything about this graph. Okay? Am I going to have any asymptotes here?
Yes.
Well, clearly I have a vertical. Do you agree? What's my vertical asymptote?
X equals 2.
Am I going to have a horizontal? No. Am I going to have an oblique or slant?
No.
Yes. How am I going to find it? Do the longer synthetic division as your first step of the problem. Okay? Let's do synthetic. So my root is 2. I put my coefficients in descending order. And now mama the problem. So what does this equal? X plus 3 plus 16 over x minus 2. And I can do a quick check by putting it back. Why do I do that first? Well, two reasons. One is I can now identify the slant asymptote, and secondly, I'd rather differentiate that. Way easier. Not even close. So, this is a transient term, isn't it? F of x is equal to this. This is not the asymptote, this is the function. The asymptote, as x gets bigger and bigger and bigger, this graph is going to look like y equals x plus 3. So I'm going to identify my slant as y equals x plus 3. Not that part, that's part of the function. Okay? My function, this is my function. My asymptote is the linear part. So when I start and draw my graph, I'm going to put these two asymptotes before I do anything else. Okay? Because that'll tell me where everything's going to be put. Now I need to take a derivative. I can take a derivative of the original quotient, and that's fine, but it'll take me a while to factor. It's too much work. No, take a derivative of this. Way easier. What's f prime of x? Well, let's see. 1 minus 16 over x minus 2 quantity squared. If it helps you, think of it as 16 times x minus 2 to the negative first power. Because that derivative should only take one step. Okay? What do I want to do with this? I want to set it equal to 0. Well, if that's true, then doesn't that mean that 1 equals 16 over x minus 2 quantity squared? And doesn't that mean that x minus 2 quantity squared equals 16? So doesn't that mean that x minus 2 equals plus or minus 4? So therefore x equals 2 plus or minus 4, which is what? Negative 2 or positive 6. By the way, at this point you should probably check. If x is 6, then that's 6 minus 2 or 4. 4 squared is 16. 1 minus 16 over 16 is 0. If x is negative 2, negative 2 minus 2 is negative 4. When I square that again, that's positive 16. Boom. Okay. Always a good idea to do a quick check. That one worked very nicely. I have 2 critical values. Negative 2, positive 6. Okay, let's work with that. So what am I putting on my f prime line? I'm putting negative 2, I'm putting positive 6. Am I putting anything else? Anything else on my number line? 2, because we can change sign where the denominator is 0. I can't evaluate it at 2, but on one side or the other of 2, I can change sign. In fact, how often are you going to change sign at a vertical asymptote? Exactly 50% of the time. You don't know ahead of time. Did we in the last problem? Yeah. So I have 4 intervals I have to consider. All right. Which version do I want to use? It doesn't matter. I'll use this one right here. This is the easiest one. So x is hugely negative. That means my denominator is astronomically large, which means 1 minus that is going to be tiny. So it's positive. Let's do the same thing on the other side. X is astronomically large, then my denominator is astronomically large, so 1 minus that is really close to 1 again. Now, let's get really close to 2. If I'm really close to 2 on the negative side, like 1.8, 1.9, 1.99, this is a really, really, really tiny negative number, but now I'm squaring it. So it's an even tinier positive number. 1 minus 16 over tiny positive number is a huge negative number. And the same thing. I did a lot of calculating, didn't I? No, don't do any calculating. Just come up with signs. So this is an interesting one, isn't it? Do I change direction at any point on this graph? Yeah, it appears I changed direction a couple of times. Are both negative 2 and 6 in the domain? Are they happy points? Yeah, they're horizontal tangents. So I'm actually going to have a max and a min. Oh, cool. This graph's got all sorts of cool stuff happening. So f is increasing negative infinity to negative 2, and then again from 6 to infinity. F is decreasing negative 2 to 2, and then again 2 to 6. I cannot make that one interval because I'm not defined at 2. I have a vertical asymptote at 2. Wow, this is getting more interesting every moment, isn't it? Think we need to do the second derivative? Probably be wise. All right, so if my first derivative, if it helps you, rewrite your first derivative like this. 1 minus 16, how about if I write it as x minus 2 to the negative 2? That'll make the second derivative a little bit easier. So then what's my second derivative? 32x minus 2 to the negative 3. Yes? Does this ever equal 0? Never equals 0. So I only have one number to consider, 2. Now, big negative number, I have a negative denominator. This is negative. Big positive number, I have a positive denominator. Positive. So f is concave up from 2 to infinity. f is concave down from negative infinity to 2. Okay, do I have any inflection points? I changed concavity here. Do I have any inflection points? No, because there's a vertical asymptote. I changed concavity where there was a vertical asymptote. We did that in the last problem too, didn't we? So I changed concavity, but at the vertical asymptote. There's no inflection points. But I have a couple of potential extrema. Okay, so let's address this. I don't need this anymore. F of -2, f of +6. Let's go ahead and calculate those. I'd easier to put it in here. If I put a -2, then that's -4. I think that's -3. -2, so +1, -4. Okay. I put in a +6, and that's 9 plus 4, that's 13. All right. As x grows without bound positively, do you agree this is going to approach positive infinity? As x grows without bound negatively, this is going to approach negative infinity, because again, the degree difference is 1. So am I going to get any absolute extrema?
No.
No, they're both going to be local. I'll just go ahead and say it. Is a local max or min?
Max.
Max.
Min.
Min. Houston? I don't think we did that right.
You need to switch the numbers around.
Did I switch them around?
Yeah.
Or switched.
Which is which?
Your local max and local min need to be just switched. So 13
Should
on
I-
the bottom, -3 on the top.
Oh, thank you, thank you. I wrote it somewhere. How did I screw that up? You're right. Okay, now it's even weirder. Tell me why this is weird.
Smaller numbers than the max.
How can the max be smaller than the min? What kind of math are you guys doing? Oh, wait a minute, there's a whole set of weird stuff happening in this problem. Is that even possible that I could have this happen?
The vertical asymptotes.
Told you this is gonna be cool. You guys, the level of cool hasn't hit you yet. It'll hit you later. Whoops.
It's a crazy graph.
Ah. All right.
I'm just lost. Because I spaced out.
Now I'm gonna go ahead and change this real fast.
You can drop the thing down too.
Hold on, I'm gonna change this really fast.
Wait.
Okay, I'm not done yet. Oh, I lost a plus sign. I'll put it in there soon. You can't see what's going on here yet, so let's pull.
Much better.
Eventually. I had a room I used to have to hook my briefcase to the end of this to get a good catch. Come on. I'm gonna get angry at you. That works? No, it doesn't work.
It's
Austin, you have magic hands?
You gotta like.
Well, it worked a moment ago, as for over and over again. All right, let's finish this guy, and my denominator is. Okay, so here's our graph. This is why you never do it on the graphing calculator first, because no part of this graph is actually going to show up.
Yeah.
Why? Well, I'm being really clever and deceitful at the same time. Let me back up a little bit. What is it, 2? So let's go. Oh, yeah. By the way,
Holy welcome.
my min, you see the min? Max? That's why the min is higher than the max. They're in two completely separate pieces of the graph. But do you see any asymptotes here? Well, let me back up a little bit further here. Isn't x equal to one of them? Can you now start to see x equal 2? But what was the other one? You see it? It's right there. You see the line? Come on, you got it. That's cool. You don't see it here, but if I were to draw this, this is how I would actually draw it. If I was doing it by hand, because back in the day I had to do this by hand. Desmos has made me very lazy, just so you know. All right, so what are our asymptotes? Equal 2, y equal x plus 3, so it's about like that. We said we had a, what was it, f of negative 3 was equal to, f of negative 2 was equal to negative 3. And then f of 6 was equal to 13, about right here. This is how we used to do in the old days. I didn't have to plot any other points. I needed to have those important points. And because these are asymptotes, I just have to have it approach the curve. Now, is that the graph we just came up with here? Yeah. Did I need to do that in order to do this? No. What did I need to do this? I needed to know where it was increasing, decreasing, and concavity. What did our intervals of concavity say? I was concave up in this region. I was concave down in this region. We were told it increased from here to here, and again from here to here. We were told it decreased from here to here, and here to here. And then we had our maxes and mins. So we did everything we needed to draw this graph really well without plotting points, other than the highs and lows, knowing where they were. Now, doing it on the computer almost feels like cheating at this point because we know how to do all the pieces. So this is where a slant asymptote comes in. And as I back up, you can all see the behavior. So today was not about asymptotic behavior in general. It was very specifically lines, asymptotes. That is confusing. An asymptote is a line. I have asymptotic behavior to a line. Asymptotic behavior just means I look like another curve. Next semester, a significant amount of your Calc 2 will be based on asymptotic behavior. No lines. No lines at all. You're going to be able to draw sine waves and cosine waves, and either the x's using polynomials and showing the relationships. It's crazy stuff. Crazy stuff that I could take a sine wave and do a polynomial that looks essentially the same. We've done that in this class already. I demonstrated it. And so that's the asymptotic behavior, non-lines. Today is just the lines that I want. So that's basically everything you need to know about graphing, really, in a nutshell. That, again, find the critical values, find the intervals of increasing, decreasing. Find your second derivative critical values, find the intervals of concavity. Now find your maxes and mins either using the first or second derivative, find your inflection points. If there are asymptotes, where in the game do you want to identify the asymptotes? Where do we do it here? At the very beginning. Because if there are asymptotes, that will help later. Don't find them after the fact, find them first. Do most of the graphs have asymptotes? No. I probably need a quotient or something else going on. Most of your graphs won't, but if they do, I want to be able to clearly identify them. Okay? Any questions?